Hello and welcome. The goal of this presentation is to support regional teams in implementing the IUCN Red List of Ecosystems, or RLE, for coral reefs as part of the ongoing Global Assessment Project. The presentation will provide an overview of the key steps involved in conducting regional RLE assessments and guide you through the critical stages of the process. We'll start with a brief introduction to what the RLE is and how it works, and the main outcomes from a regional coral reef RLE assessment. We will then walk through the technical aspects of the assessment in more detail, starting with how to define your units of assessment. From there, we'll explore what to consider when describing your ecosystem, including how to develop a conceptual model to frame your understanding of the ecosystem's structure and function. We'll then cover the core steps involved in assessing criteria A through D, including how to set collapse thresholds. Finally, we'll show you how to determine the overall risk status for each of your assessment areas. By the end of this 1-hour presentation, you should have a clear understanding of what's needed to carry out a regional coral reef RLE assessment. Since this is a long presentation, it may be better to view it in sections. Let's begin with a bit of background on what the Red List of Ecosystems actually is. The RLE was developed by the IUCN as a standardized science-based method for assessing the risk of ecosystem collapse. Many of you will already be familiar with the IUCN Red List of Threatened Species, which identifies the risk of extinction for individual species. The RLE applies that same concept, but to ecosystems rather than species. It is now recognized as the global standard for evaluating ecosystem risk and can be applied to any type of ecosystem, whether terrestrial, freshwater, marine, or subterranean. Importantly, the RLE was recently adopted as a headline indicator in the Kunming-Montreal Global Biodiversity Framework, reinforcing its role in global biodiversity monitoring and policy reporting. For those looking to dive deeper into the methodology, a comprehensive explanation of the scientific foundations and assessment rules can be found in the updated guidelines for the RLE, available on the official RLE website. Unlike species which can go extinct, ecosystems don't simply disappear. Instead, collapse refers to a major transformation where the ecosystem loses its defining features, structure, or function, and is replaced by a fundamentally different ecosystem. This may have some elements in common with the previous ecosystem and may be valuable, but is no longer considered the same ecosystem due to the loss of its essential components or interactions. Ecosystem collapse represents the final stage of ecosystem decline. Here, we've included images of some real-world examples of ecosystems that have either collapsed or degraded so severely that they've effectively transformed into a completely different ecosystem. The Red List of Ecosystems framework consists of 5 criteria which together offer a comprehensive, multi-dimensional approach to assessing the risk of ecosystem collapse. Each criterion captures a different aspect of ecosystem change, from spatial patterns to the integrity of ecological processes, allowing for a holistic evaluation. Criterion A focuses on reductions in the ecosystem's distribution over time. This includes both historical declines and projected future losses. It helps identify ecosystems that have already shrunk significantly or are likely to in the near future. Criterion B looks at ecosystems with restricted geographic distributions that are exposed to existing or potential threats. This criterion captures systems that may not be declining yet, but are highly vulnerable due to their limited range. The next 2 criteria focus on the internal condition of the ecosystem. Criterion C assesses environmental degradation, specifically the deterioration of key abiotic features like water quality, temperature, or soil conditions that support the ecosystem. Criterion D examines disruptions to biotic processes and interactions. This includes loss of characteristic species, shifts in community structure, or the breakdown of ecological interactions that define the ecosystem. Finally, Criterion E applies quantitative risk analysis. This involves modelling the probability of ecosystem collapse over time, using scenarios and simulations to forecast risk based on current trends and uncertainties. Together, these 5 criteria provide a robust and flexible tool for assessing ecosystems across all types and regions. Once one or more of the 5 criteria have been applied to assess an ecosystem using the appropriate steps, rules, and quantitative thresholds outlined in the methods, each ecosystem is assigned a risk category that reflects its likelihood of collapse. There are 8 possible risk categories, ranging from ecosystems that are thriving and healthy to those that have already collapsed. At the most severe end is collapsed, the ecosystem equivalent of species extinction. This category is used when an ecosystem has lost its defining features and functions and no longer maintains its identity. Below that, there are 3 threatened categories which indicate a high-risk collapse: critically endangered, endangered, and vulnerable. Ecosystems that are not currently threatened may fall into one of several other categories, such as near threatened, least concern, or data deficient, the latter used when there isn't enough information to confidently assign a status. This classification system provides a consistent way to communicate ecosystem risk, support conservation prioritization, and guide management and policy responses. Here we show a visual representation of how the different RLE risk categories might look when applied to a coral reef ecosystem. On the far right, we see a reef classified as least concern, a healthy functioning ecosystem. It has a high cover of live hard corals, low levels of macroalgae, and a high abundance of key fish groups like groupers and parrotfish. As we move from right to left across the image, the reef's condition deteriorates and its risk of collapse increases. We see declining coral cover, increasing algal dominance, and a noticeable reduction in fish populations, particularly those species critical for maintaining reef health and structure. Eventually, we reach the collapsed category on the far left. At this point, the reef has lost its defining features. There is little to no live hard coral remaining. Fish populations have been largely depleted, and the structure is dominated by other taxa, such as algae or sponges. Regional Red List of Ecosystems assessments can produce outcomes at multiple spatial scales. Using the Western Indian Ocean example, at the broadest scale, a regional risk status for coral reefs across the entire Western Indian Ocean was produced. This was disaggregated into 11 distinct coral reef ecoregions, with each one assigned its own risk status based on the condition of coral reefs within that ecoregion. To better understand why a particular risk category was assigned, the results could be further explored by individual criteria. For example, here we show results from the Comoros ecoregion, highlighting the risk status assigned under each of the RLE criteria, A through D. We can zoom in even further to look at the specific indicators used under Criterion D, which focuses on biotic processes. This detailed breakdown shows which components of the ecosystem were most at risk and contributing to the overall risk status. And finally, at the finest scale, we can explore reef site level declines for specific indicators assessed under Criterion D. In this example, the coloured points on the map present the magnitude of hard coral cover decline at individual reef sites across the 4 coastal counties of Kenya. For instance, green points show sites with no decline and purple sites show collapsed sites. These multi-scale outcomes help inform conservation policy and management at multiple levels, from regional frameworks to national strategies and local reef action plans. Now that we've explored the background of the Red List of Ecosystems and the value of undertaking regional coral reef assessments, we will shift our focus to the technical implementation of the RLE framework. In this section, we'll walk through the key steps involved in applying the RLE to coral reefs of your region, using examples from the Western Indian Ocean assessment. We'll begin by discussing the chosen study areas, then how to define units of assessment, that is, how to decide on the spatial boundaries and scale at which ecosystems will be evaluated. Then we'll look at how to describe your ecosystem, identifying its defining features, ecological processes and key drivers of change. We'll also cover how to develop a conceptual model, a simple but powerful tool that helps frame your understanding of how the ecosystem functions and how different stressors may be impacting it. And finally, we'll delve into the core of the assessment, how to assess criteria A through D, including how to select appropriate indicators and define collapse thresholds. Before diving into the technical steps, it's important to briefly highlight the role of stakeholder engagement in the assessment process. Engaging regional coral reef experts through virtual or in-person workshops and maintaining communication and involvement throughout the process helps to building a strong, credible assessment grounded in local knowledge. In addition, involving a range of experts can help to build a broader regional consensus on things like selecting indicators, setting collapse thresholds, and working out baseline values for these indicators. They're also key when it comes to providing data, validating coral reef layers, defining your assessment units, and shaping what is included in the conceptual model. It's also essential to involve decision makers, to inform them about the process, its relevance, and how the results can be used. Sharing results with them before publication helps build trust and increases the likelihood of uptake into policy and management. The goal is to apply the Red List of Ecosystems framework to coral reef regions across the world, contributing to one of the first global ecosystem assessments of its kind. This will be a bottom-up approach with regional teams leading regional assessments of their own coral reefs. The idea is to ensure that each RLE is tailored to local contexts, making the results directly relevant for regional and national policy and planning. In most cases, the work will be led by the regional GCRMN node, or another regional group or organisation with the capacity and expertise to coordinate the effort. In total, 10 regions around the world will be supported to carry out these assessments. When beginning an RLE assessment, one of the first and most important steps is to identify the ecosystem to be assessed. To ensure standardization across regions and to meet global standards, we will use the IUCN Global Ecosystem Typology. The Global Ecosystem Typology is a comprehensive classification framework for Earth's ecosystems that integrates their functional and compositional features. It is an accepted international standard under several United Nations conventions. It categorizes ecosystems according to hierarchical levels, starting with the realm the ecosystem occupies, then the biome, and finally the functional group it is part of, which is related ecosystems that share common ecological drivers and biotic traits that characterize the group, for example, temperate woodlands. There are 3 lower levels of classification, level 4, 5, and 6, which can be derived from the subdivision of ecosystem functional groups. For this global assessment, all regions will assess photic or shallow coral reefs, which are part of the marine shelf biome. That means deep water or mesophotic or rocky reefs will not be considered. Next, we must define the units of assessment, the spatial areas within which you'll evaluate ecosystem risk. To achieve this, photic coral reefs need to be disaggregated to level 4 of the typology, regional subgroups. These subgroups represent compositionally distinctive geographic variants that occupy different areas within the distribution of a functional group. Using the global ecosystem typology in this way ensures that the regional assessment fits within a consistent global structure, while still being tailored to the specificities of each region. To identify these regional subgroups, the starting point for each regional coral reef assessment is the marine ecoregions of the world, as defined by Spalding et al. 2007. These marine ecoregions are based on broad biogeographic patterns and marine features, not just coral reefs. Therefore, these can be adjusted to better reflect coral reef-specific boundaries by lumping or splitting ecoregions. The goal is to define units that make ecological sense for coral reef systems. When determining whether to adjust the default ecoregions, ask yourself, are there unique biotic communities or environmental conditions that set them apart? Are there oceanographic processes like large currents or rivers and other large features which create natural boundaries? Do the coral reefs in this area face distinct threats compared to neighbouring areas? And can we clearly describe these differences? It's essential that your units are spatially meaningful. If they're too broad, you risk masking important variation. If they're too fine, you may trigger Criterion B, which flags small or fragmented distributions, even when it's not ecologically justified. A good example is the outer and inner reefs of the Great Barrier Reef. These have different biophysical conditions, face distinct threats, and support different coral communities, meaning they could be more appropriately assessed as separate units. For the Western Indian Ocean assessment, the Marine Ecoregions of the World framework provided a broad biogeographic foundation for defining assessment units. However, to make the units more relevant to coral reef ecosystems, the team also integrated insights from two coral reef-specific bioregionalizations. The first was OBERA 2012, which focused specifically on coral reef diversity and structure in the Western Indian Ocean, and the second was Veron et al. 2015 from the Corals of the World work, which provided a global coral biogeography perspective based on coral species distributions. Using these frameworks together allowed a refinement of the marine ecoregions of the world boundaries, making minor adjustments where necessary to better reflect the ecology and diversity of coral reef ecosystems. In the end, the region was divided into 11 subgroups or distinct coral reef ecoregions, each representing a unit of assessment at level 4 of the IUCN Global Ecosystem Typology. Each region should consider using any existing local or regional coral geographic distributions that could help refine or improve the definition of the coral reef ecoregions to be assessed. A key step in the Red List of Ecosystems assessment process is writing a detailed ecosystem description. This provides the foundation for selecting indicators and applying the RLE criteria. As mentioned previously, this assessment focuses purely on photic or shallow coral reef systems. The ecosystem description should provide a broad ecological overview of coral reefs in your region, in their undisturbed state, while also highlighting the unique features and characteristics of each distinct coral reef ecoregion. The ecosystem description should cover the following elements: the distribution of coral reefs across the region, the characteristic native biota, including dominant and functionally important taxa such as hard corals, the abiotic environment, such as depth, water temperature or substrate type, and the key ecological processes and interactions within and between the biotic and abiotic components. Once this is complete, a description of the main threats and how they are affecting the reefs across the region will be required using the IUCN threat classification scheme. To help illustrate all these aspects, assessors will develop a conceptual model. This is a visual tool that distills how the coral reef ecosystem functions, showing the relationships between the biotic and abiotic components, pressures and responses. Helpful guidance for constructing a conceptual model is available in the RLE guidelines. In addition, a theoretical collapse state needs to be defined, which is when the condition of coral reefs are considered to be collapsed. That is, the coral reefs are no longer functioning as they should and have transformed into another state, e.g. an algae-dominated reef. For example, the collapse point can occur when hard coral cover is below a certain minimum level, or ocean temperatures exceed a certain value, or algae cover is above a certain threshold. A good conceptual model should be comprehensive, but also intuitive and easy to follow. It helps communicate the ecosystem's structure and dynamics and supports transparent decision-making throughout the assessment. When developing your model and description, it's important to include features specific to coral reefs in your region. For instance, in the Western Indian Ocean, fleshy algae are considered the dominant space competitors to hard corals. But in other regions, this might be soft corals or sponges, and these differences should be reflected in your ecosystem model and description. Finally, the recommendation is to create a single regional coral reef conceptual model, rather than developing a separate model for each ecoregion or unit of assessment. The Western Indian Ocean assessment highlighted the following key biotic components: hard corals as the primary ecosystem engineers, macroalgae, the main space competitors to corals, herbivorous fish, which play a critical mediating role controlling algal growth, and piscivorous fish, which provide trophic regulation across the reef food web. The conceptual model should include all features which are considered important, even if they are not evaluated as part of the assessment due to a lack of data, for example. In the Western Indian Ocean, major pressures such as ocean warming were formally assessed in the RLE process. Other pressures like sedimentation and coastal development were recognised as important and hence included in the model, but were not assessed due to data limitations across parts of the region. These threats were shown in grey. This helps to highlight data gaps and improvements that could be addressed in future assessments. The model should include any important biotic threats as well, such as crown of thorns starfish or invasives such as lionfish. Here are examples of models from other coral reef RLEs, which you can use for reference when building your own, specifically the Caribbean, Mesoamerican reefs, and Colombian Caribbean reefs. This model is not from an RLE, but may provide an idea of other features and processes that may want to be considered when developing your RLE model. Now we move on to applying each of the RLE criteria individually, including the main steps and considerations involved in the process. For the global coral reef RLE assessment, each region will follow a common approach based on the methodology from the Western Indian Ocean assessment. This helps to streamline the process and ensure consistency in how the criteria are applied and comparability of results across the global assessment. This approach makes use of global datasets, including satellite-derived temperature data and open-source spatial layers such as the Millennium Coral Reef Mapping Project. It also uses biotic indicators which can be derived from data from GCRMN monitoring programs, as well as other regionally available monitoring datasets. Before we get into the nitty-gritty of each criterion, it is important to note that each criterion can be assessed in various ways, known as sub-criteria. Criterion A, which looks at the change in ecosystem distribution, can be assessed across these different timeframes, while the other ecosystem distribution criterion, B, can be assessed in 3 ways. For this specific assessment, we will cover depths for A1, B1 and B2. For the 2 process and integrity-based criteria, C and D, we will examine changes over 50-year periods, that is, the past 50 years for C1 and D1, and the next 50 years for C2. This approach ensures a comprehensive assessment of both spatial and functional dimensions of coral reef ecosystem risk. Criterion A aims to assess the reduction in the distribution or extent of an ecosystem over time, typically over a 50-year period. In some ecosystems, this can be straightforward. For example, in the Aral Sea shown here, reduction in ecosystem extent is clearly visible by comparing maps or images over time. However, coral reefs present unique challenges. While there are satellite-derived maps of reefs, such as the Millennium Coral Reef Layer, there isn't a consistent, geographically exhaustive time series of reef extent over the required time frame, 50 years. Even more critically, coral reefs can undergo functional collapse without any visible change in the structural extent mapped by satellites. For that reason, using mapped area reduction doesn't work well for coral reefs. To address this, we will adopt a proxy indicator to measure change in reef extent. We will use hard coral cover and measured the proportion of reef sites with less than 10% hard coral cover, which is an estimated minimum threshold for net accretion. Because there is uncertainty around this threshold value, we applied a sensitivity analysis, testing coral cover levels from 1 to 10% in 1% increments to evaluate the effect on racification, as shown in this figure from the Western Indian Ocean. Each line represents a different ecoregion and shows the proportion of sites which fall below different hard coral cover thresholds. For this project, we are exploring ways to improve this approach to make the proportion of reef sites which have collapsed more spatially explicit, therefore providing a closer representation of the reef area which has functionally collapsed. Criterion B is used to identify ecosystems whose geographic distribution is so limited that they are at risk of collapse due to the chance occurrence of one or a few threatening events, such as a cyclone, bleaching event, or disease outbreak, completely wiping out the ecosystem. To assess Criterion B, the Red List of Ecosystems framework uses two standardized spatial metrics: extent of occurrence, EOO, the area within the outer boundary of the ecosystem's known distribution, and area of occupancy, AOO, the actual area occupied by the ecosystem measured in grid cells. To begin, you'll need to provide a validated coral reef layer for your region. We will start with the Millennium Coral Reef Mapping Project layer, as curated by the UNEP World Conservation Monitoring Centre. However, you can include localized corrections or replace parts of the global layer with more accurate or detailed national maps where available. Once the coral reef layer has been validated, the process to calculate EOO and AOO is fully automated using scripts in the RLE code repository. The script will generate the minimum convex polygon for EOO and count the number of occupied 10 by 10 kilometer grid cells to calculate AOO. In addition to the spatial extent, you must also identify whether there are current or expected threats affecting coral reefs in each ecoregion, such as warming, pollution, coastal development, or overfishing. Finally, to determine the risk category, you'll compare your EOO and AOO values to the thresholds set in the RLE guidelines, which are summarized in these tables. These thresholds determine whether an ecosystem should be classified as vulnerable, endangered, or critically endangered under Criterion B. Criterion C evaluates the degradation of abiotic features that support an ecosystem's structure and function, such as temperature, water quality, nutrients, or hydrology. To apply Criterion C, you should assess relative change over time, typically over a 50-year time frame, either through past data or future projections. The goal is to evaluate whether these abiotic conditions have changed to such an extent that they compromise the ecosystem's ability to sustain its characteristic biota and ecological processes. Abiotic degradation can be measured using time series of environmental data, spatial comparisons to reference sites, or modelled scenarios of continued change. For example, in rivers, you could assess flow alterations or oxygen decline, while in lakes, consider nutrient loading or salinity increases. Standard thresholds in the RLE guidelines help determine the level of risk based on the magnitude and severity of degradation and the proportion of the ecosystem affected. Regions can explore abiotic decline over the past 50 years as part of Sub-criterion C1. The RLE code repository will include functionality to analyse trends in SST over the past 50 years, but regions can also assess other threats such as sedimentation, coastal development, or pollution. But remember, for any indicator, you must be able to define a collapse threshold and have data over a broad enough spatial and temporal extent in the region. Here is a hypothetical example for how to approach assessing Criterion C1 by looking at the change in sea surface temperatures over the past 50 years. Through remote sensing, there is SST data extending back around 30 years for most coral reefs. To assess Criterion C1, we need to select an appropriate indicator of ecosystem collapse, and a key part of this step is identifying a meaningful collapse threshold. Two possible SST-based indicators are the SST anomaly, which is the change in temperature relative to a defined baseline, and the mean SST. For the anomaly, we can draw on global targets, such as the Paris Agreement goal of limiting warming to below 2 degrees Celsius above pre-industrial levels, to help define a plausible collapse threshold. For the mean SST, each region could determine an absolute SST threshold beyond which coral survival becomes untenable. Once a collapse threshold is established, the time series can be extended or hindcasted back to the start of the 50-year period, that is 1975. We can then evaluate the degree of temperature increase since 1975 relative to today and the collapse threshold using this formula, and estimate proportion of coral reefs currently exposed to elevated temperatures. This method is still under development and once finalised will be made available through the code repository. Following the Western Indian Ocean assessment, each region will assess Sub-criterion C2, which evaluates the projected degradation of abiotic conditions over the next 50 years. For coral reefs, the main threat affecting their persistence into the future is ocean warming, which causes widespread and severe coral bleaching and mortality. Each region will use modelled climate projections to assess future degradation, specifically projections of annual maximum degree heating weeks, DHW. The relationship between degree heating weeks and coral bleaching and mortality is well established. The specific indicator used to measure the decline is the number of years in a decade where DHW is high enough to cause severe and widespread bleaching. For the Western Indian Ocean, both 8 and 12 were used because they are globally recognised benchmarks for severe coral bleaching. Each region can select the DHW value that best represents severe bleaching in their region, taking into account any expected regional adaptation or acclimation. Once a DHW level is decided, for each ecoregion, calculate the number of years where the maximum DHW exceeds the bleaching severity limit in the current decade, i.e. from 2020 to 2030, and in 50 years, i.e. from 2070 to 2080. The relative severity of decline of the abiotic environment in the next 50 years is calculated using this formula. To complete this calculation, it is necessary to define a collapse threshold, the point where the reef ecosystem can no longer maintain its identity or recover. For example, in the Western Indian Ocean, 2 major bleaching events per decade, i.e. exceeding the DHW threshold twice every 10 years, was used as the collapse threshold. This equates to 1 major bleaching event every 5 years, which if sustained would limit recovery and lead to continued degradation and collapse. By using DHW values averaged across the entire ecoregion, the analysis captures 100% of the coral reef extent within each ecoregion. As a result, the calculated relative severity of decline can be interpreted using the top row of the severity extent matrix to determine the final risk status under Criterion C2. Criterion D focuses on identifying ecosystems that are experiencing severe disruption to their biotic processes and interactions. This includes declines in characteristic species, shifts in community structure, or loss of ecological functions that are essential for the ecosystem to maintain its identity. The method used by the RLE to assess biotic degradation is the relative severity of decline. This method evaluates how close each ecosystem component is to collapse or severe disruption over a specified time period, in this case, 50 years. Effectively, it gives a measure of where each component is today, relative to both the state of the reef 50 years ago and a hypothetical collapse point where that biotic component is considered no longer functional. This approach helps identify which aspects of the ecosystem are most degraded and how that degradation contributes to overall risk of collapse under Criterion D. To assess Criterion D, each region should follow a structured process to identify appropriate biotic indicators that reflect the health and functioning of the coral reef ecosystem. Begin by revisiting the characteristic native biota identified during the development of the conceptual model. Review the available data which could relate to these biota, such as monitoring data collected through GCRMN nodes or other regional sources. Next, identify key biotic indicators that can be derived from the available data. Common examples include live coral cover, fish biomass, species richness, abundance of functional groups, e.g. herbivores, predators. Establish a baseline reference state, typically representing conditions from 50 years ago, to serve as a starting point for assessing decline. Define a collapse threshold for each indicator, the point at which that component is no longer providing its essential ecological role, and the ecosystem is considered functionally disrupted. Finally, select indicators that have sufficient data, a clear reference state, and a defined collapse threshold. Now let's look at how ecosystem components and indicators were selected for Criterion D in the Western Indian Ocean assessment, an approach that other regions can adapt to suit their own context. In the Western Indian Ocean, 4 key components of the coral reef ecosystem were assessed using data collected through standard underwater survey methods like point intercept transects and belt transects, compiled by the regional GCRMN node. First, hard corals, which are the primary ecosystem engineers, forming the structural foundation of coral reefs. Second, macroalgae, which compete with corals for space and can overgrow and dominate reefs under degraded conditions. Third, herbivorous fish, which play a vital role in controlling algae. And finally, piscivorous fish, which help regulate the food web and contribute to overall ecological balance. For each of these components, a suitable indicator was selected based on what data were available. Hard coral cover was used since it has been the principal measure of coral health over several decades. For algae, the Western Indian Ocean team used the coral to algae cover ratio rather than algae cover alone. This was to reflect the competitive dynamic between corals and algae and how dominance can shift as reefs degrade. In this case, algae included a mix of turf, calcareous and fleshy algae due to inconsistencies in how algae types were identified across different monitoring programs. But this can be adapted. For instance, if you have consistent data, you might use only fleshy algae for your indicator. For herbivory, parrotfish abundance was used. This was a practical choice because much of the regional fish data was only identified at the family level, and parrotfishes, or Scarinae, were one of the most consistently recorded herbivore groups in the available datasets. For piscivory, grouper abundance was used because over 80% of the piscivorous fish recorded in the Western Indian Ocean datasets were groupers, making them a good proxy for this trophic group. Now, the key things to consider when selecting indicators are: use indicators that are ecologically meaningful in your region. Make sure there's enough data in terms of spatial coverage to support the analysis. For fish indicators in particular, abundance was used in the Western Indian Ocean because the data were available across much of the region. But if you have biomass data, that's even better. It's a more sensitive indicator of ecosystem condition. And if your fish data are available at the species level, then you can go a step further and calculate broader metrics, such as total herbivore biomass, instead of relying on parrotfish alone. So while this is how it was done in the Western Indian Ocean, each region should select components and indicators that reflect their unique ecosystem dynamics and the data they have access to. Now that we've covered the ecosystem components and indicators used under Criterion D, let's talk about how collapse thresholds were set and the rationale behind those decisions. For each indicator, it's essential to define a realistic collapse threshold, that is, the point where the loss of that component would mean the ecosystem has lost its function or identity as a coral reef. It marks the boundary between a functioning system and one that's fundamentally changed. For the benthic indicators, this threshold reflects the point at which the reef has transformed into something else, for example, from a coral-dominated reef to one overgrown by algae. In other words, it's no longer functioning as a coral reef. For the fish indicators, the threshold reflects a point where the ecological process they represent, such as herbivory or piscivory, is effectively no longer functioning. That might be due to fish abundances being too low to have any meaningful ecological effect. Now, how do you decide on this threshold? Ideally, you'd use values from published studies that show how ecosystem condition or function declines relative to these indicators. But if the evidence isn't available or doesn't fit your region, you can run an expert elicitation process. The important thing is to get regional consensus on what these values should be. In the Western Indian Ocean, the team applied consistent thresholds across all assessment units. But there's flexibility. If you have strong justification, for example, if some ecoregions naturally have lower coral cover, then you can set different thresholds for those areas. Just make sure you document the rationale clearly. So let's walk through the thresholds that were used. For hard coral cover, a threshold of 5% was chosen. This implies that when coral cover drops below 5%, the reef is considered collapsed. This sits between the commonly cited 10% threshold for net reef accretion and more extreme thresholds like 1% or less, which were considered too low as significant ecosystem function would already be lost by that point. For the algae to coral ratio, the threshold was set at 0.833, which means algae cover is 5 times higher than coral cover at collapse. At this ratio, coral recovery becomes highly unlikely and the reef is essentially locked in an algae-dominated state. For the fish abundance indicators, parrotfish for herbivory and groupers for piscivory, there was no exact value in the literature that defines a collapse point. So the Western Indian Ocean team used a percentage of the initial or baseline value from 50 years ago, specifically 10% of the reference parrotfish abundance and 20% for groupers. This approach meant that the actual threshold value varied by ecoregion depending on their historical baselines. But the principle was the same. When abundance drops below the threshold, the ecological role of that fish group is assumed to be effectively lost. To assess each biotic indicator under Criterion D, you'll need to establish 3 key values: the collapse threshold, which we covered earlier, the current condition of the indicator, and the initial or baseline value from around 50 years ago, so around 1975. This step focuses on how to estimate the current value for each of your biotic indicators under Criterion D. It requires coral reef monitoring data from which you calculate the current indicator value for each reef site, for example, the hard coral cover or parrotfish abundance at a site. It is important to determine a cutoff point for the inclusion of sites to get an estimate of the current state as closely as possible. For example, you may choose to only include sites with data from the last 5 years. The window allows you to include sites which may not have been surveyed in the latest round of monitoring, but which still have fairly recent data, thereby increasing your sample size. You can then select the most recent value for each site within this window, or average across all surveys at a site during that period. Next, we will discuss how to estimate that initial value, which acts as the reference point for measuring the severity of biotic degradation over time. If you're fortunate enough to have data from around 1975 for your indicator, for example, survey records showing average hard coral cover at that time, then you can use that data directly. That's the ideal case. However, as was the case in the Western Indian Ocean, long-term monitoring data from the 1970s are often scarce or non-existent. So the Western Indian Ocean team explored 2 alternative approaches. If you have a good time series of monitoring data spanning at least 20-30 years, you can use statistical methods to hindcast and estimate conditions around 1975. You don't need to have 50 years of data for every site. A few well-monitored sites might be enough to represent the baseline for an assessment unit. In the Western Indian Ocean, there weren't enough reef sites with sufficient time series data for hindcasting. So instead, the team had to consider another way to estimate indicator values for the 1970s. The experts made a couple of decisions based on their understanding of the ecosystems. 1, reefs in the 1970s were generally in a better condition than today. And 2, that 1998, the year of the first widespread coral bleaching event, marked a turning point for reef condition in the region. Therefore, prior to 1998, most reefs were assumed to still be in relatively good health and representative of conditions from the 1970s, with only a few localized areas already degraded. The team undertook a literature review, compiling data from some of the earliest reef surveys in the region, typically from the 1980s and 1990s. They then selected reef sites known to be healthy prior to 1998 and representative of wider reef conditions in each ecoregion or unit of assessment. Using these pre-1998 data on live coral cover and algae cover, They calculated a mean value and a range for each benthic indicator for every ecosystem unit. This gave them an estimated baseline to compare current conditions against, allowing them to calculate relative severity of decline for Criterion D. So in your region, you'll need to follow a similar process using either long-term data to hindcast or historical records and expert input to build the best possible estimate of reef conditions 50 years ago. Note that conditions in the 1970s for reefs may have been worse than what they are today. Now let's focus on how to establish baseline values for the fish indicators. As with the benthic indicators, it may be challenging to get quantitative monitoring data on reef fish populations going back 50 years. In the Western Indian Ocean, for example, no long-term datasets existed for parrotfish or grouper abundance from the 1970s. If you do have long-time series data for some sites, you could attempt to hindcast and estimate what fish populations looked like 50 years ago. There may also be estimates of intact or pristine fish populations in the literature from research, which you could use as well. But in most cases, that won't be possible. So the approach used in the Western Indian Ocean was to apply a space for time substitution. This method assumes that fishing pressure was much lower in the 1970s than it is today. Based on that, it's reasonable to infer that fish populations were higher across most reef areas in the region. To estimate these historical values, reef sites located within well-managed, no-take marine protected areas were used. These areas typically have higher fish abundance because of limited or no fishing and can serve as a proxy for historical fish populations, essentially representing what reefs may have looked like in the 1970s before widespread fishing pressure. Each team can identify one or more reference MPA sites in each unit of assessment that are well protected, representative of other reefs in the ecoregion, and have data on the indicators being used. If there are no protected sites with data in a particular ecoregion, you can look to other comparable sites with similar reef structure and oceanographic conditions. You may also find estimates in the published literature that give historical context for reef fish populations in your region. These estimates are not exact and must account for natural variation across reefs, so they should incorporate some uncertainty. Therefore, it's important to calculate a range around the mean, for example, a standard deviation or confidence interval. Now, let's briefly dip into some of the technical details of how the Western Indian Ocean assessment applied initial values when calculating the relative severity of decline for each indicator under Criterion D. The method allows you to account for uncertainty in the estimated initial value from literature or reference sites and apply it across all reef sites with current data. Here's how it worked. In this example, for hard coral cover in the northern Mozambique, southern Tanzania assessment unit, the estimated initial value for hard coral cover from the 1970s was for 40.2%, with a standard deviation of 16%. Using bootstrapping, an initial value was randomly drawn for each reef site from a normal distribution with this mean and standard deviation, for example, 37.2%. That randomly drawn initial value is then applied to all coral reef sites within the northern Mozambique, southern Tanzania assessment unit, and together with the current hard coral cover values for all sites, the relative severity of decline for each site was calculated using this formula. We then check what proportion of sites fall into different severity brackets. For example, sites with 30% severity, sites with 50% severity, sites with 80% severity. Using the standard RLE matrix, we determine the risk category for that iteration based on the highest threshold exceeded. Extent in the matrix refers to the extent of the ecosystem, which in our case was the proportion of sites. Therefore, for example, to get a critically endangered classification, 80% or more of the ecosystem must have declined by at least 80%. An important point to make here is that we generally assume our reef monitoring sites are representative of the full extent of the ecosystem within each ecoregion, and that's because they tend to be well distributed and cover all major reef areas. But if there are large areas of the ecosystem that aren't covered by survey data, we need to take that into account. For instance, if all your data comes from the southern half of the ecosystem, you need to ask whether those sites reasonably reflect what's happening in the northern half as well. If both areas face similar threats, then it might be fair to assume that the trends are comparable, but that assumption should be based on some level of justification. Anyway, back to using the matrix to determine a risk category. If 51% of sites have a relative severity 50%, then it is vulnerable. If 70% of sites have declined by 30%, then it is least concern. And if only 10% of sites have declined by 80%, it is also least concern. The highest risk category triggered in that iteration becomes the provisional classification, in this case, vulnerable. This process is then repeated 749 more times, each time randomly selecting an initial value using the ecoregion mean and standard deviation for a total of 750 bootstrapped iterations. For each iteration, the classification is recorded. At the end, you count how many times each risk category was produced. In our example, 5 iterations produced vulnerable, 743 iterations produced least concern, 1 iteration each produced near threatened and critically endangered. Because least concern was by far the most frequent outcome, the final classification for the ecoregion was least concern. This approach helps ensure that the uncertainty around historical baselines is explicitly considered in the final RLE risk assessment. Now that we've assessed each indicator independently, we need a way to determine the overall risk status for Criterion D for each ecoregion. One straightforward option is to take the highest risk status across all the indicators. Essentially, whichever component is doing the worst determines the risk status for the whole criterion. However, in the Western Indian Ocean assessment, we used a stepwise approach which provides a more nuanced picture. In this method, we assess the risk status of each ecosystem component in the order of their ecological role, starting with corals, because corals are the architects of the reef. Then consider algae as the primary competitors to coral, followed by parrotfish, which mediate algae and coral balance, and finally groupers, which provide top-down control as piscivores. As you move through this sequence, the risk status can be raised by a single category if the next component in the sequence is in a higher risk category than those before it. This way, the system avoids being overly influenced by any one component. This method gives the most weight to coral cover, recognizing its foundational role in reef function, while still acknowledging the importance of other biotic components. It also tempers the overall contribution of the fish indicators in driving the final risk status. And importantly, it allows for additional components to be added in future assessments if relevant data becomes available. Let's walk through a worked example using the Northern Tanzania and Kenya unit of assessment. We've assessed the 4 indicators under Criterion D and have the following risk statuses. Coral cover is classified as least concern. The algae to coral ratio is near threatened. Parrotfish are also near threatened. And groupers are between endangered and critically endangered. We begin with the indicator that comes first in the ecological sequence, coral cover, and that's our starting point, and it's at least concern. Next, we look at algae, which are near threatened. That's 1 level above least concern. So we move the overall risk status up 1 level from least concern to near threatened. Then we look at parrotfish, which are also near threatened. Since that's the same as the current overall status, we stay at near threatened. Finally, we examine groupers, which are at endangered to critically endangered. That's clearly higher risk than near threatened. So again, we move the overall status up 1 level from near threatened to vulnerable. So the final risk status under Criterion D for the Northern Tanzania and Kenya unit of assessment is vulnerable. Now let's run through another example, this time for the West Madagascar ecoregion. Corals were assessed as near threatened. Algae to coral ratio came out as vulnerable. Parrotfish were also vulnerable. And groupers were again vulnerable. We begin, as always, with corals, which are at near threatened. The next component in the ecological sequence is algae, which are assessed at vulnerable. That's one level higher than near threatened. So we move the overall status up one level to vulnerable. Parrotfish are also at vulnerable, so the status remains at vulnerable. Groupers are also vulnerable, so again, there's no change. So by the end of the sequence, the final risk status under Criterion D for West Madagascar remains vulnerable. Once you've completed your assessment under each of the applicable RLE criteria and sub-criteria, whether that's A1, B1 and B2, C1 and C2 or D1, the final step is to determine the overall risk status for coral reefs in each ecoregion. To do this, you apply a precautionary approach, which is a core principle of the Red List of Ecosystems framework. Essentially, you look across all the individual risk categories assigned under each criterion, and you take the highest or most severe of those risk categories as your final risk status for the ecosystem. So, for example, if under Criterion A your coral reefs are endangered, and under Criterion B they are vulnerable, and the risk under Criterion C is least concern, and finally, under Criterion D it is near threatened, then the final risk status for that coral reef ecoregion would be the most severe category assigned across all of the criteria, which in this case is endangered. This method ensures that any critical or severe risk identified through one criterion isn't diluted or overlooked in the final assessment. That concludes this presentation on applying the Red List of Ecosystems to coral reefs as part of the Global Red List of Coral Reef Ecosystems project. Thank you very much for your attention. We hope you found it useful and that it has provided a clearer understanding of the technical steps involved in the assessment process. Please feel free to reach out to us with any questions or if you need any further clarification.